Hello, geometry scholars. Today, we're going to be kind of extending using similarity to solve similar triangle problems. And we are actually going to do justifying similarity. So the basic question that we're going to see in this skill is over and over again, are these triangles similar? Why are these triangles similar? So a good but not like a better or best explanation would be the triangles are similar because they have the same shape and different size. So the question that we're going to explore right now is how can we craft a better, more precise explanation? So there's really three parts towards building a very good quality explanation. First, what I'd like to see is if you have sides that are marked, I'd like to see you test out the ratios and kind of see, is there a consistent scale factor that's being applied? So that way the sides are proportional to one another. Then we're going to identify corresponding angles that are congruent to each other. And then we will also discuss how to choose an appropriate triangle similarity theorem. So let's actually kind of build a good explanation with this one. So the first thing that I would do immediately is test out the sides. So we can see that HF matches with FW. So I'm going to kind of use top over bottom triangle. And then we have also that GF from the top matches with the FV from the bottom. So now we're just going to put in the numbers and see how they work. So HF is 63. Over 4 or over 7. It's the FW. And then GF is 36. And FV is 4. What I like to kind of do here, so some people actually kind of just simplify the fraction. So, you know, this is equal to 9 to 1, 9 over 1. But 63 divided by 7 is 9. 36 divided by 4 is 9. You can also see that this simplifies to 9 over 1. So the sides are proportional. All right, then we're going to do the angles. And the only angle that we have that's marked that we can use are these vertical angle pairs. So I could actually say that angle HFG is congruent to angle VFW. And then we could actually use a triangle congruence similarity theorem. And if we kind of notice here, I have a side, I have an angle in the middle, and then I have a side out here. So we would say that the triangle FWV is similar to triangle FHG. So the symbol here means similar to. So just by kind of looking at the side ratios and seeing that they're the same, naming the congruent angle in the proper order, and then putting a proper theorem basically almost helps us create a proof level type of response. And if you had this type of response on your homework or on the upcoming mastery you have a really good, well sorted out, well reasoned response. All right, in the next few slides, we're actually just going to give you the written examples here. So I would encourage you to pause the video and make sure that you have the major theorems down for similarity. So obviously, if you have no angles at all, the only theorem that you can use is the side, side, side. And what we can actually see here is that if I am maybe doing small triangle over big triangle in this case, I look at the corresponding matching sides. So the 5 matches up with the 10. So 5 over 10 is equal to 0.5. 7 over 14 is equal to 0.5, and 9 over 18 is equal to 0.5. So we're good. So if all the lengths of the corresponding sides of the two triangles are proportional, then the triangles are similar. All right, if we have an angle that's between two sides, then we don't need to look at the third side. So if you have two corresponding sides, you do need the angle that's in between, hence the name side, angle, side. Now, the good news is that if you have, so you can pause this and make sure you have these theorems down, but we will go on. The angle is really nice because if we have two pairs of corresponding angles that are congruent to each other, we don't even need to look at the side ratios to say that they're similar. So this is why we don't have angle, angle, angle. We just have angle, angle similarity postulate. All right. Let's actually look at an example now that's a little bit more interesting, maybe proving. So it's asking us, is DEF similar to the smaller triangle? One thing that I like to do with these overlapping is I kind of like to redraw so that they're kind of two separate triangles. So this is going to be EDF, and that's 11 and 8. And then I have VDW. And if this is 2, that means that this has to be 6. So the first thing that I would do is test side ratios. So we can see quite nicely if we do big triangle over small triangle, and I always like to put, what triangles I'm comparing, just so that my ratios can be nice and consistent. So my big triangle is 11, and my small triangle is 8. And I'm going to put a question mark over the equal sign. So I want to see, is that the same as 8 over 6? Now, if I go to my calculator and I find out what these ratios are, so I got 11 divided by 8, that's about 1.375. And then 8 divided by 6 is 1.33. Now, these look almost the same, but they are not quite the same. So this is not equal. So therefore, the triangles are not similar. So on your homework question, it will be kind of framed as, are these triangles similar or not? And then you could even just write, not similar in the blank. Now, if these side ratios did work out, you do have that shared angle D from both triangles. That does work out quite nicely. Another type of problem that you're going to see is using similarity. So we say that these triangles are similar, so you're going to have to be able to solve. So I really like this problem, and back when we were teaching in person, this was kind of a staple in this lesson, and it's called the distance across a pond problem. So there's a surveyor. So a surveyor is not necessarily a person that gives like statistical surveys, but somebody who actually surveys the land to kind of for the purpose of like map making and measuring, distances and stuff. Now, obviously, the surveyor can't go in the pond. I mean, there's probably leeches or something like that, so he can't, measure inside of a pond. But if he could like measure the distance out here, then he could kind of get the distance across the pond. So when you have this type of situation, I circle, and we kind of already did label. So BC is 60, CS is 48, DS is 52, and AD is 65. And the question is, what is AB? One thing that is helpful is to kind of look at the total distance. This is going to be 108, and then 65 plus 52 is equal to 117. So I'm just going to kind of redraw the triangles. So I'm just going to kind of start with the small triangle. So I got CD and S. This is 52, 48, 40. And then I'm going to just draw the big version, so the ABS. That's 117, 108, and question mark, or you could call it X. So maybe I'll do small over big. So the 48 matches with the 108. And then the 40 matches the question mark. And what's nice is I can stop there because I can just cross multiply. And when I cross multiply, I just circle what I'm multiplying. So I got 108 times 40. And I'm just going to get my handy calculator out here. We got 4320 equals to 48 question mark. And then I'm just going to divide by 48. And then I get that question mark is equal to 90. Now I challenge you, this is not the only way to do this problem, but I challenge you to think about, are there other ways in which you could do this problem? So if you're looking to challenge yourself a little bit more, I encourage you in your notes even to think about maybe some alternative ways that you could solve this problem as well. Because when I do this problem in class, I actually usually give the students a little time to think about this on their own and see what they come up with. And I have seen multiple ways at getting that question mark equals to 90. And don't forget to put the units on there as well, so you can keep your science teacher happy. So that pretty much covers it. So you'll have similar or not questions with the justification. So please use the checklist to help you justify. And then we'll have some problems that will say, the triangles are similar, can you solve for the missing side? And that is section 8.3 in a nutshell.